Hello students, I am Isha Medhirata. In today's video, we are going to discuss Einstein's theory, which is important for understanding laser, and we'll also be discussing some basic terms which are related to laser. So let's start with Einstein's theory first. Before starting with Einstein's theory, I would like to tell you about Einstein's coefficients, which are dependent on the three processes which were proposed by Einstein. That is, number 1, induced absorption, number 2, spontaneous emission, and number 3, stimulated emission. So B12 is known as probability of induced absorption per unit time. So it's a process which occurs when atom moves from lower to higher energy level, absorbing some energy. The second coefficient is A21, which is known as the probability of spontaneous emission per unit time. And the third one is B21, which is known as the probability of stimulated emission per unit time. Just have a look at the three coefficients. The first one and the last one are the two coefficients in which external energy is required, and so the alphabet used is B. The constant used is B. But the first one is from lower to higher, so we write 1, 2. The third one is from higher to lower, so we write 2, 1. And the second process where the constant A is used is without any external energy. Now, I'll start with relation between the Einstein's coefficients, that is, how are B12, A21 and B21 related to each other. So we'll start with thermal equilibrium. In thermal equilibrium, whatever are the number of upward transitions means upward transitions are from lower to higher level. That should be equal to the number of downward transitions per unit volume per second. So whatever atoms are moving from ground state or from lower to higher, the same should come from higher to lower. That means rate of absorption should be equal to the rate of emission. What is rate of absorption? B12N1 rho, because absorption is only of one type, that is induced absorption. And what will be the rate of emission? Now we have studied two different emission processes. Two processes were proposed by Einstein, spontaneous emission and stimulated emission. So if we are saying rate of emission, it should be addition of both. So A21N2, that means spontaneous emission, should be equal to B21N2 rho, that is stimulated emission. Now what have I done is, I have taken all the terms containing rho on one side because that is radiation and I will be making radiation as my subject. So B12N1 minus B21N2 rho is equals to A21N2, and this gives me my first equation, that rho means the density of radiation is equals to A21N2 upon B12N1 minus B21N2. So this is the first equation we have derived. Now if I divide this equation by N2, I will be getting A21 upon B12 N1 by N2 minus B21. Now what do I do is, I know what is N1. What is N1? N1 is known as the population of lower energy level, right? What is population? Number of atoms in lower energy level. What is N2? It is known as the population of higher energy level. That means number of atoms in the higher energy level, right? So N1 and N2, with the help of Boltzmann distribution law, they can be written by these two equations. N1 is equals to N0 e raised to minus E1 upon kBt, and N2 is equals to N0 e raised to minus E2 upon kBt. N0 means ground level, population of ground level. N1 means population of lower energy level and N2 means population of higher energy level. So when we are considering lower energy level, the corresponding energy E1 is considered, and when we are considering higher energy level, the corresponding energy E2 is considered. What is Kb? Kb is known as Boltzmann constant. Value is 1.38 into 10 raised to minus 23 joule per Kelvin. Now from these two above equations, I can derive the equation of N2 by N1, or I will be getting N1 by N2 in the equation of rho. So N2 by N1 is equals to e raised to minus E2 minus E1 by kBt. But I know that E2 minus E1 is equals to h nu, right? The difference of energy levels represents the energy of photon emitted. So I can write N1 by N2 is equals to h nu by kBt. So this equation I substitute in the equation of rho, and I get A21 upon B12 e raised to h nu by kBt minus B21. Now what do I do is, I just take out the term B21 from the denominator common. So I will be getting A21 by B21 upon B12 by B21 into e raised to h nu by kBt minus 1. I have simply divided by B21 in the numerator and denominator, or you can say I have taken out B21 common from the numerator, from the denominator. But from Planck's theory of radiation, there is equation of density of radiation defined as rho is equals to 8 pi h nu cube upon c cube 1 upon e raised to h nu by kBt minus 1. What is this h? Planck's constant. What is nu? Frequency of radiation. What is c? Speed of light. This is the equation of density of radiation from Planck's theory. But Einstein also derived an equation which we named as equation number 2. So if we compare these two equations 2 and 3, we get that the numerator term A21 upon B21 should be equal to 8 pi h nu cube upon c cube, and B12 should be equal to B21. What do you mean by this equation? B12 is equals to B21. B12 means the rate of induced absorption and B21 means the rate of stimulated emission. That means for these two equations, if we are comparing these two equations, we should have the rate of induced absorption equal to the rate of stimulated emission. And we know that laser is possible only if there is stimulated emission. So this equation also says that whatever is the induced absorption taking place, this should be equal to the amount of stimulated emission, only then laser is possible. So probability of absorption is equal to the probability of stimulated emission. Now let's see, this was a requirement that B12 should be equal to B21. But then Einstein tested whether it actually happens or not, whether B12 is equal to B21 or not. So what did he do was, he compared the two types of emission processes. So he compared R21 stimulated and R21 spontaneous by taking the ratio. So R21 stimulated upon R21 spontaneous, both the equations are written. This gives B21 rho upon A21. From the equation 2 which we had written, we know that rho is equals to A21 upon B21, 1 upon B12 upon B21 e raised to h nu by kBt minus 1 to 1. So substituting all this, we derive the equation of B21 rho upon A21, and this gives us R21 spontaneous upon R21 stimulated is equals to e raised to h nu by kBt minus 1. Just cross multiply and you can say that spontaneous term is on one side and stimulated multiply by a factor on other side. I can say from this equation that my spontaneous emission is overpowered or spontaneous emission is more as compared to stimulated emission. But then how will I get laser? Because for laser, stimulated emission is required, right? So laser action, if I want to achieve laser action, I will have to increase the stimulated emission, because according to the comparison of the two emission processes, he concluded that spontaneous emission is more. And if spontaneous emission is more, we all know that spontaneous emission cannot be controlled. Spontaneous emission is incoherent. It is scattered in different directions. Then how will laser be achieved? So what we have to do is, what Einstein proposed is that we have to increase the stimulated emission. So now I'll move on to some basic terms which are related to laser before we study what laser is. So the first term is known as population inversion. You know, comparing the two emission processes, he came to know that stimulated emission is less compared to spontaneous emission. So he proposed a process that if you invert the population means if I achieve more number of atoms in higher energy level, and continuously if I give radiation, I will have more stimulated emission. Only then laser is possible. So he said that the state of achieving more number of atoms in higher energy level as compared to lower energy level, that is N2 greater than N1, is the meaning of population inversion. This is exactly population inversion. You can see from the earlier diagram, E1 has huge number of atoms compared to E2. So in this case, if I give external energy, I will be getting more induced absorption and spontaneous emission. But on the other hand, just see the diagram below. There are more number of atoms in the higher energy level. In this case, if you supply radiation, more stimulated emission is going to take place. So what we have done is we have inverted the population. We have increased the number of atoms in the higher energy level. How do we do that? How do we increase the number of atoms in higher energy level? It can't happen on its own. So that requires a process called pumping. The mechanism of exciting atoms from lower energy state to higher energy state by supplying external energy from any external source is called pumping. Now, pumping depends upon the type of materials also. What is the base material in which we require population inversion? So depending upon that, you can have optical pumping. Optical pumping means you are exciting atoms by using a light source. Then you have electrical pumping, in which you give a high electric current. And third is known as the direct conversion pumping. Direct conversion pumping is, say for example, I give you an example of a semiconductor laser. In this, higher is the forward bias condition, higher will be the excitation level of atoms. So it's a direct conversion of one energy to other energy. Now we'll discuss a process called lazing, the third term related to laser. So first thing is we require population inversion. Once population inversion with the help of pumping is achieved, we will get stimulated emission. So the process which leads to the emission of stimulated photons after population inversion is called lazing. Next we have lifetime. Now till now we have discussed the terms, I have been repeating that higher energy level, lower energy level, right? But just assume I consider a state in which my atom is having 100% energy. 100% energy means fully charged. You know, higher the energy of atom, higher is its instability. More energy atoms are highly unstable. The moment they reach to 100% energy level, they suddenly come down. So lifetime is a term which tells us the maximum time period for which an atom remains in the higher energy level, that is the excited state. And this lifetime is around nanoseconds because stability is very low. These atoms are highly unstable when we talk about excited states. Moving on to the next term, that is metastable state. Now we know that stimulated emission is a process which requires external energy, and it's a process where your atom should have some time to stay. Only then it can absorb energy and come down. Now just consider an atom in 100% energy level. First thing, it already has 100% energy. It cannot absorb more. Secondly, the lifetime of an atom in 100% energy level is nanoseconds. It hardly can stay in this excited state. So for stimulated emission to occur, your atom should be at a comparatively stable level, which is below 100% energy level. This is known as the metastable state. Why I say that stimulated emission occurs at this process, at this state? Because first of all, it is not having 100% energy, so it can absorb more. And secondly, the atom has a larger lifetime, around a millisecond. 10 raised to minus 3 to 10 raised to minus 2 seconds is the lifetime of this state. Because if the atom can stay there for a larger period, only then you can control a process called stimulated emission. So I would say actual stimulated emission starts from metastable state. Here, the lifetime of atom is large. Now coming on to active medium, that is my next term. So I require a medium in which there are atoms, and these atoms I can I require population inversion in these atoms, only then stimulated emission is possible. So the medium where population inversion is achieved is known as active medium. It can be a solid medium, it can be a liquid medium, it can be a gaseous medium. Optical resonator is the next term which is very important when we are discussing laser. Now, the full form of laser has a term called amplification. So how is laser amplified? It is amplified with the help of optical resonator. So what is an optical resonator? It is a pair of reflecting surfaces, particularly mirrors. The reflecting surfaces are mirrors, out of which one should be a perfect reflector and the other should be a partial reflector. Means one should reflect 100% light back into the same medium, and one would partially reflect light and would partially transmit it. Understood? Let's see what an optical resonator is. So you can see the diagram below. There is a dark blue colored mirror shown, which is a full reflecting mirror, and a light blue colored shown. From there you can see emerging laser beam. So in this, what actually happens is that suppose you have achieved population inversion, stimulated emission has started, and the photons are emitted. The photons, when strike at the full reflecting mirror, they come back into the medium and they excite more atoms. Getting it? So this is how, like, one photon excites one more atom. Now 2 will give 2 more, so there are 4. 4 will give 4 more, so there are 8. And this is how your laser will be amplified. Understood? Let's have a look at a small animation. You can see here that one side, the left portion, has full reflecting mirror and the right side has partial reflecting mirror. In between them you can see the number of atoms are growing and the number of photons are coming out only from the partial reflection mirror. So this helps in achieving amplification of a laser beam. Clear? So today we have discussed Einstein's theory. We have discussed the ratio of the two processes. We concluded that stimulated emission is less compared to spontaneous emission. So how do we achieve it? For that we have studied some basic terms which are very important for laser. Hope you have understood all the topics I discussed in today's video very well. Thank you.